Before we actually start with the material of the course, I want to go through a quick review of some fundamental relations that we see in quantum physics, some relations, or if you want, some equations, and also some concepts. And if you feel that you're already familiar with the most basic fundamentals of quantum mechanics, you can skip this video and you can go to the actual part related to the material on decoherence and so on. So you can skip this video if you feel you are familiar with the concepts of quantum mechanics. Otherwise, you might take this as just a quick overview of the fundamentals. So I would like to start, in particular, I would like to start from the concept of wave function. For example, we might have a wave function which depends on the variable r. This is the vector r with the components x, y, z. For example, you might think of this as a position of the particle and then time. And in particular, the mode squared of this wave function, which is a complex function, multiplied by the volume element d3x. So you might think of this as dx, dy, dz. This gives us the probability to find the particle, for example, in a small volume d3x. So if you want here, I might also put d3r. Using the mode squared of the wave function, for example, it is possible to calculate averages, and we can say that the average position of the particle can be calculated in this way. We have the vector r, and then we have the mode squared of psi rt, mode squared d3r, or d3x if you want, and this can also be written in another type of notation, for example like this, psi star, which is the complex conjugate of psi, and then we have the operator r acting on the wave function psi, d3r. So when the operator r acts on psi, we actually get the vector r times psi. So you can also put this r on the left of psi star. So this is just some notation, and I don't want to get into all the details of quantum mechanics. You should already be familiar with some quantum mechanics. I'm just trying to recap some of the most important concepts. It's just a quick overview. Then the wave function psi of rt can also be rewritten in the following fashion. In particular, we can think that we have a superposition, then we have coefficients of the kind c sub n that depend explicitly on time, and we have eigenfunctions phi sub n of r. So you can see that the dependence upon t and r is separated when we do this expansion. Phi sub n, for example, is an eigenfunction of a certain operator a. If I apply the operator to phi sub n of r, I obtain a scalar a sub n phi sub n of r. We can assume that such functions are orthonormal, which means that if I integrate phi sub n of r star phi sub m of r d3r, I get delta nm. So this is the Kronecker delta nm, which means that I get 0 if m is not equal to n, and this means that these two functions are orthogonal, and their mode, in particular their mode squared, if n is equal to m, is equal to 1, because the Kronecker delta gives us 1 when n is equal to m. Whereas these coefficients, c sub n of t, in particular their mode squared, is equal to a probability, p sub n, which does not change over time. And the average of a certain operator a in the state psi can be calculated by using the expressions that I have given above, but let me just quickly skim through the math here. I have a summation over n of p sub n a sub n, where this a sub n is this coefficient here, whereas this p sub n is this p sub n here, and this is equal to summation over n mod c sub n squared a sub n. Another important thing to mention is the fact that we also have the so-called bracket notation, and for example we might have a bra of the kind f denoted like this, and then we take the inner product with a ket denoted like this. This is equal to, by definition, g f, but with a star, so I take the complex conjugate of this, and this can also be represented in the continuous domain. So with an integral I have f star of r g of r d3r, where instead of using the ket g, I'm using the function g of r, whereas instead of using the bra f, I'm using the function f star, so I have the complex conjugate of f of r. And indeed, a bra or a ket, if you want, they can be thought of as vectors, just like a function. A function that depends on a certain variable can be thought of as a vector, and in this case, of course, it is a vector with an infinite dimension. So we have an infinite number of points which cannot be counted, so they are uncountable. And this is another way of thinking of a certain inner product in this infinite dimensional domain, which is very important in quantum mechanics. With the bracket notation, instead of using an expansion of this kind, we have something like this. We have the ket psi of t, which depends only on time. Pay attention to that, and I will get back to the relation between this object and the wave function that depends both on time but also on space. And this can be thought of as a summation over n c sub n of t, which is actually the same as this one. And then here we have some ket n. So this replaces this function phi sub n that depends on r. So it's a different vector, but you can think of this as some basis over which we are expanding our function psi of t, our ket psi of t. In particular, we can find, for example, the coefficient c sub n of t by taking the inner product between n and psi of t. But this can also be calculated, if you want, with an integral. So we can also calculate it from such an expression, for example. And we have something like integral over phi star sub n of r psi rt d3r. And we can also use the so-called completeness relation, which we can write by using these two identities. In particular, we can also rewrite psi of t like this. So if we rewrite such a coefficient in here, and we can put n in the at the front, we have summation over n written as a ket, then we have n written as a bra, and we have the inner product with psi of t. But since what we have on the right should be equal to what we have on the left, and that's equal to psi of t, you can see that such an object should be equal to an identity. So I will write it as 1, like this, but that means that this summation should be an identity. And in matrix and vector notation, this is like taking a tensor product between a certain vector n with itself. So here you can see that we have a vector n, we have another vector n, we take the tensor product and we have to sum over the vector. So we can, for example, use the subscript j to denote the fact that we have different vectors, and this summation should be equal to the identity matrix in a certain, in this case, infinite dimensional space, but I'm using this notation for convenience if you are more familiar with that. And something similar can also be done in the wave function domain, let's call it that. We have psi of rt, which replaces this ket, and this can be written as summation over n phi sub n of r, and then we have such an integral. Remember that this would be the coefficient c sub n, which is exactly the expansion that we wrote earlier, like this. But now I'm going to write the integral, and we have something like phi sub n star. Remember that we only have to sum over n because the others are simply orthonormal, and in particular it is something that I have not written down. There is also another relation, and the relation is of this kind, summation over n of phi star sub n of r phi sub n r prime equal to the Dirac delta in a certain so if for example r is in a three-dimensional space, the Dirac delta would be a three-dimensional Dirac delta of r minus r prime, and this would be given by the Dirac delta of x minus x prime times delta of y minus y prime times the delta of z minus z prime, like this. So there is also this fundamental relation. And here let me write down the expression. I have phi sub n star of r prime psi of r prime t d3r prime. And indeed, since what we have on the right should be equal to what we have on the left, you can see that the only choice is indeed this one, the one that I have just written down. We have to impose such a relation so that this equation is consistent, and you can easily check that. And using the notation that we have developed so far, we can also rewrite, for example, operator A acting on psi of t, and we can rewrite it as A summation over n, the ket n, the bra n. So this is the completeness formula, which means that this is just the identity. And then here we have psi of t, like this. Now when we act with A on n, we get A sub n, and therefore we can also rewrite this as summation over n A sub n like this, and then I can put a parenthesis like this, and I have psi of t. And remember where we started from such an expression, and this means that what we have inside the parenthesis should be equal to A. So this is an expansion, if you want, of a certain operator in terms of its eigenvalues and the basis n, as you can see. And if you want, we can also rewrite the average that I wrote earlier, the average of A in the state psi, which you can take this as a definition. You sum over n, you have the probabilities, c sub n mod squared, A sub n, and this can be written as the summation over n, inner product between psi and n, which is, this would be c sub n star, and then you have n inner product psi, and this would be c sub n. So this would be c sub n squared, mod squared, A sub n, and this can also be rewritten in the following fashion: psi summation over n A sub n psi. And what we have in here is just A. So you can see that indeed this average can also be computed in the following manner. We take the inner product between psi and A applied to psi. So sometimes it's simply denoted like this, and if you think about it, if you if you're already familiar with some quantum mechanics, this should make sense. Then another important concept that we have in quantum physics is the concept of hermeticity. So when we consider Hermitian operators, Hermitian, why are they so important? Well, because let's start from a simple definition. So an operator is said to be Hermitian if the operator is equal to the complex conjugate transpose of the operator itself. So you can think of the operator as a certain matrix. You take the complex conjugate and then you transpose, or vice versa. You can take the transpose and then the complex conjugate, and these two should be equal. And this is an important property because, for example, if you take an inner product between a bra that we call U, then we have the operator A, which we assume to be Hermitian, and then we act with A on a certain ket vector that we call V. Then, since this is a number, because it is a certain inner product, just like the one that you see in linear algebra, for example, like this, U transpose, and then you have a matrix applied to a vector. But in this case, we have to be a little bit careful because this U, denoted like this, is a certain vector transpose, but also complex conjugated. So we have to be a little bit careful with that. And since this is a number, and in particular in quantum physics it is important that the number is not just a number, but it is a real number. We want a real number because that is something that we expect of our observables. The observables are related to the eigenvalues of a certain operator. So we expect that, we want to impose that this number is a real number. So it means that if we take the complex conjugate of that, in particular we take the complex conjugate transpose of such an expression, so this is a number. So if we take the transpose, of course that remains the same. But we must also take the complex conjugate. So it means that we take the complex conjugate transpose of that, and we can denote it like this. V goes on the left, then we have A transpose complex conjugated, so there is a symbol for this, and in particular it is denoted as A with a dagger. So we have A dagger, and then we have U, like this. And since A dagger is equal to A, here we can put A, we can write it like this. So this means basically that if we have an inner product of the kind U, and then we have A acting on a certain vector V, which I can also denote like this without this bar, and this is just a simplification of the notation. So we act with A on the state V, and then we take the inner product with U for an Hermitian, for a Hermitian operator. This can also be written as the inner product between V, and then A acts on U, like this, if A is equal to A dagger. This is a constraint that makes sure that A has real eigenvalues, which leads to real observables in physics. And I think that this is it for this video, because otherwise it would be too long. We actually went through some important properties of operators, observables, eigenvalues, wave functions, and the bracket notation, and so on. So let's see if I still need some more concepts, and after that we can get to the actual material of the course.